So we still have a few more exponential equations to look at. We're going to look at a few examples that involve e to the x or e to a power, where e is the base of the natural exponential function. So these are actually going to come out kind of nice overall. If you look at this first example, solve e to the minus x plus 4 minus 2 equals 6. We're still going to use the same approach, method 2, where we want to isolate the exponential expression. So I'm going to add 2 to both sides here, right? And I get e to the minus x plus 4 equals 8. Now I have the exponential isolated, so I can take ln of both sides. And now I'm going to apply the third law of logarithms to bring that exponent out in front as a factor, right? And negative x plus 4. I got to write in parentheses times ln of e equals ln of 8. So here's where there's something new. Somewhere in our list of properties, we've written down that ln of e is always equal to 1. So it's nice to work with ln and e together, because sometimes nice things happen to us. Here we end up with negative x plus 4 times 1 equals ln of 8, or of course just negative x plus 4 equals ln of 8. And so negative x is equal to ln of 8 minus 4. If I multiply both sides by negative 1, I get x is equal to negative ln of 8 plus 4. And that's my solution. So this magical step with ln of e is equal to 1. Somewhere, again, in our list of properties of logs, we said log to any base of that base to the first power is 1, or just that base by itself is 1. And so this is how that property manifests itself with natural log and the natural exponential e. And so I think that's sort of worth highlighting and definitely worth memorizing at this point, because it's going to come in very handy in things that we do in the future, especially with applications. And, decimal. Negative ln 8 plus 4 is about 1.92. I did that ahead of time on my calculator, so I'm going to let you check that on your own. Okay, let's do another. Solve 4e to the x plus 9 is equal to 1. Okay, so looks awful innocently not complicated, right? I got to subtract 9 first. Sorry, start by subtracting 9. So we're working our way in toward the exponential. We have 4e to the x equals negative 8. Now I would divide both sides by 4, right? We're going to take 4e to the x equals negative 8 and divide both sides by 4 to isolate that e to the x. So I get e to the x equals negative 2. Okay. Now it looks kind of simple and innocent, but there's something a little weird going on here, because when you take a base to any base to a power, or when you look at any exponential function, the output is always a positive number, right? we never can take e to a power or any positive base to a power and get a negative, even if x is negative. If x is negative, e to a negative power is still going to come out to be a positive number. So I would say e to the x is greater than 0 for all x. So we're kind of in trouble here. And just in case you don't spot that, say you didn't notice and you kept going and you said, I'm going to take ln of both sides. You would get x ln of e equals ln of negative 2. There's our 1. Ln of e is 1. X is ln of negative 2. But here, there's no such number. So if you didn't notice that the exponential can't be negative, you do have to notice that ln of negative is not possible, because the domain of a logarithm function consists of positive numbers only. So the result has to be written this way. There's no solution. So this is something you will need to recognize. And there are two spots in this problem where the trouble shows up. You might catch it right back here. There's no way e to the x can be negative. That's impossible. You could stop there if you recognize that. Or if you keep going, you try to take ln of a negative, and that you can never take a log. Any log of a negative number is never defined. It's not possible. There's no solution to this equation. Okay, we're going to look at one more of these. And it's sort of a weird example, and I go back and forth on whether to even include this or not, but we're going to do it. And it's sort of interesting, but it is kind of a very special kind of situation. There's some of this on the homework too. Solve e to the 2x minus 2e to the x minus 15 equals 0. And what's unusual is we have, I think we have two unlike terms involving e. And so there's a trick to solving this kind of problem. And this doesn't fit into either of the two methods. That's why I kind of hesitate to even bring this one up. But let's go ahead and talk about it. There's a trick here. The trick, let's call it that. The trick is to think of that e to the 2x as e to the x squared. Okay. That's true. They're equal to each other. So our equation can be written as e to the x squared minus 2e to the x minus 15 equals 0. And we can get a handle on this by making a substitution. And it doesn't matter what letter I use here. I guess I'm just going to use a letter capital A equal e to the x. So I'm going to replace e to the x here and e to the x here down below by making that substitution. So I'm going to have a squared minus 2a minus 15 equals 0, or just a squared minus 2a minus 15 equals 0. So what's kind of interesting here is this turns into a quadratic type of equation. We're not solving for a, we want x, but we can use what we know about factoring to break this problem down. We can actually try factoring this quadratic in a into, it's not too hard to see, this will factor into a minus 5, a plus 3 equals 0. You can check to see that works out. So that allows us to take our original equation and split it into the two separate smaller equations by the zero property, right? A minus 5 equals 0, or a plus 3 equals 0. Now, when you use a substitution technique like this, what you now do is we substitute back. We're going to go back to what a originally represented, which was e to the x. So we can say e to the x minus 5 equals 0, or e to the x plus 3 equals 0. And now method 2 kicks in. So our standard method where we isolate the exponential in each case. So e to the x here is equal to 5, or e to the x is equal to negative 3. And then we apply our taking ln of both sides principle, right? ln of e to the x equals ln of 5, or ln of e to the x equals ln of negative 3. And I think we're getting trouble in this out of this second factor. We'll talk about that in a moment. Ln of e to the x is x ln of e equals ln of 5. There's that ln of e that is equal to 1, right, that we've seen popping up. So we have x times 1, or just x, is ln of 5. There's a solution to our equation. And on the other side, we have x ln of e equals ln of negative 3. Again, that's just x, but the problem is there's no such number as ln of negative 3. It's impossible to take ln of a negative, just like it's impossible for e to the x to take a negative value. So we actually get no solution out of that part of the problem. There's only one solution, ln of 5. And I guess I should write a decimal down. What is that? 1.6094. That's about 1.6094 is a decimal value. So that's kind of an unusual, tricky, interesting kind of problem where we were able to make a substitution and observe it's a quadratic. To me, the signal is this presence of e to the 2x and e to the x at the beginning. Otherwise, I would never guess. And I also would never, ever think to use this technique if someone hadn't shown me first. So it's definitely an unusual situation. Okay, we got one more video segment coming up in this section. We're going to talk about logarithm equations, and that's next.